Okay, great. We're going to start the first part of the after lunch panel with Matt Nobrigo, who's going to be speaking on behalf of Fish and Wildlife Service.
Thank you, Vice Chair Spivey Weber and other members of the board for the opportunity to speak. I have 15 minutes or so to put you all to sleep, I guess, being the after lunch guy. So we'll see how I do. Before I get too far into the slideshow, I wanted to give just a little sort of conceptual background building on things you heard this morning. First, I would like to state that the Fish and Wildlife Service understands climate change and its potential impacts, and we have a number of nationwide policy initiatives that are looking at ways to handle that and deal with that as best we can from a wildlife conservation perspective. But we also have the Endangered Species Act to administer, and so my talk is going to be more on that time scale. Delta smelt, as Pat Colston pointed out right before lunch, are an imperiled species. They're a listed species. The Fish and Game's index time series suggests that although they're not thriving, they can still reproduce successfully in the system right here, right now. And so that is in essence why we have biological opinions for them. And obviously, because a lot of what I'm going to be talking about is delta flow related, the water projects are the big game in town for delta flows, and so a lot of what I'm talking about then will also be related to that. So I want to make sure everybody understands that context before I start diving into things. Oh shoot, I lost my train of thought. That's terrible. Move on. I guess I'll get into key points. So our first key point is please see our April 2012 key points, which which have a lot to say about the kinds of things that Bill Fleener was talking about this morning, or long-term flow changes in the estuary and their importance to fish. For this workshop, the comments we submitted make the next 4 key points, which is we suggest the board model a range of flow objectives that could be incorporated into the water quality control plan. And then getting into the background I just gave, old and middle river flows contribute to the entrainment risk for adult delta smelt. Old and middle river flows drive the entrainment of larval delta smelt. And then multiple factors. This gets at the science panel. The Fish and Wildlife Service comments do cover a number of the changes to the low salinity zone that you heard about this morning. We recognize those. And that all of those factor into the long-term degradation of the low salinity zone, but delta outflow remains an extremely important aspect of habitat suitability, and for the purposes of what I'm presenting today for delta smelt, although it's certainly not only for delta smelt. So this is where I lost my train of thought, but I'm back on it now. So the purpose of today's workshop is to talk about what's new, basically since 2010. So although I'm kind of just rolling through ideas that are behind the reasonable and prudent alternative in our biological opinion for the state and federal water projects, I am focusing on things that are new since 2010. So this is one new thing. This is a plot that came from a court declaration of Dr. Richard DeRiso from a challenge to the biological opinion. And the punchline of the slide is high adult delta smelt salvage usually happens when OMR flows are negative and turbidity is high. And that this is the results of a model that Dr. DeRiso developed using salvage data, using the daily average old and middle river flow and the previous 3 days of turbidity at Clifton Court Forebay. And then there's a line drawn through all the bubbles are the raw data, and the bigger the bubble, the more fish were salvaged on a given day. The line is drawn probably approximately through the median, but please don't ask me that level of detail. But in essence, the biggest bubbles tend to be underneath the line. And so it was suggested that that sort of framework of combining turbidity and old and middle river flow together would make for an improvement in the in the management of entrainment of adult delta smelt. And we agree conceptually. This is some results that we've worked on since, pointing to the importance of time scale. And so this is, I think, the sort of avenue where there's an adaptive management potential in some of this. So the time step at the top, you can see the far left column is time step, and it increases from 1 day, which is what was in the plot I just showed, up to 7, which is a week, 14 days, which is where the project operators prefer to be at a minimum for trying to meet an OMR target, 24 days, which is the rough amount of time that it would take a migrating delta smelt to get from somewhere near the confluence to the State Water Project, according to a paper by Ted Summer and other authors, including me, last year, and a monthly time step, which is a monthly time step to make a point. And so the main point I want to make with the table, rather than have everybody squint at numbers and look at them, is that you can see that the number you would pick, and we picked a pretty conservative threshold here, but the number that you would pick to operate to depends on that time scale. You don't get the same answer no matter how regardless of how you average the data through time. And in every case except the longest time scale, you have to operate to a less negative OMR flow if the turbidity gets over a threshold, which is what the previous graph was showing. And the longer that time scale, the higher that turbidity threshold is. And then if you average long enough, turbidity falls out. Presumably those turbidity events that the delta smelter salvaged with don't last that long, and so you can wash them out by averaging. New science regarding larval delta smelt entrainment. This is not new science, actually. This comes from Wim Kimmerer's 2008 paper, in which he estimated the proportional delta smelt loss attributable to South Delta pumping. And this plot kind of shows two different stabs at that. The blue dots are estimates based on just running DWR's DSM-2 particle tracking model, inserting particles around the South Delta, and seeing how many are ultimately entrained, probably in a 1-month time period. And the red numbers are years from the 20 millimeter survey, where Wim had actually tried to empirically estimate entrainment loss, not using particle tracking, using fish distributions and assumptions that within a certain geographic part of the estuary they would likely be lost. And so those line up very closely. And some people have a hard time with that, because even though larval delta smelt are small, they do swim. And I am sure that that is correct, but I think what this suggests is that the net, at least in the South Delta in the spring, there must not have too much of an environmental cue to go one way or the other. And so that what this implies to me is that the net effect of all their swimming behaviors is to keep them right about where they were. And so they are, in essence, vulnerable to either net advective flows or the loss of ebb tides that Contra Costa Water District has shown can occur at negative enough Old and Middle River flows. What is a little bit new is we had not previously taken Wim's estimates and actually plotted them against Old and Middle River flow. So I asked Ken Newman in our now Lodi office to do that and look at that statistically, look at both outflow and Old and Middle River flow at the same time. And his conclusion was that the nonlinear model you cannot see in this plot, which I'm not supposed to apologize for, so I guess I'm not sorry, is the best fit, and that outflow was not really explaining any additional variation. So our newer conclusion, I guess, is that Old and Middle River flow seems to be the major driver for larval delta smelt and proportional entrainment. And as OMR becomes negative, the proportion of the larvae taken is expected to increase. This is also new. This comes from a paper that Wim did last year. and it's basically a simple kind of simulation model to show that entrainment can cause delta smelt to decline, especially given a post-pod condition in which they don't seem to hit a carrying capacity in the summer. And that not only could that happen, but that you probably wouldn't see it with like a regression analysis. So the top panel is on the x-axis, you have an increasing proportion of the larvae being lost in the simulation, and the y-axis is the regression slope that you would get plotting basically the export loss versus, or the export loss, plotting the indicator of that loss against the population. And until the confidence bands no longer straddle 0 on that y-axis, it's basically saying a linear regression would not find that. So until you're getting over 60% of the larvae entrained, you wouldn't expect a correlation to find an association between entrainment and what amounts to a pretty significant loss, fractional loss of the population. And so on the bottom plot then is the historical trend in delta smelt abundance, and then the simulated trend with only a 10% loss given modern day population dynamics. And so that's a log scale, and that begins to create a pretty large difference over time, even in training only an average of 10% of the larval population. Last topic for new science is something that people have touched on quite a bit today. The science panel touched on fall habitat, and Fish and Game touched on fall habitat, and I'm going to now also. So I'm just going to kind of try to build the story leading up to the actual new results. This is a time series of inflows to the delta from July through December, 1 month at a time. Obviously, it was very wet in 1982-83, but the take-home message here is that, by and large, there's not any real striking trend in delta inflow from the Sacramento and San Joaquin rivers. There is, however, a pretty substantial increase in delta exports over the same time period. And if that gets converted into an export to inflow ratio, that also has increased. In particular, it was kind of increasing through the 70s, and then since about 1985, it's been fairly uniformly high, often around 50% in the summer and fall. It has gone down in certain months at certain times, but by and large, it shows that kind of step change sometime around the mid-1980s. And so this is really the newer science. This is a paper that was published by my colleague Fred Feyrer and I, and a couple of other authors. I'm mentioning myself mostly, so you recognize my guilt. So I actually want to do this out of order to make the point and start down here with the bottom panel C. Which in essence the bullet is fall habitat suitability is correlated with abundance, and I'm going to make the point that of course it is, because we used the catch data to define habitat. Catch data get used to generate a fall midwater trawl index every year. We also used catch data to define habitat suitability, and the reason that works is that it turns out that delta smelt catches are correlated to water quality variables measured at the same time. So in a sense, their abundance is reflecting, to some degree, estuarine habitat conditions in real time. And that's a pretty different situation than a lot of the other sort of fish and shrimp X2 relationships where there's a flow variable during their reproductive season that is correlated with their abundance somewhere later in time. Delta smelt doesn't have one like this, but it does have one of these that's apparently a much faster operating type of thing. And that's what that bottom plot is ultimately showing, is that although it's a loose correlation, there is an association between more habitat and more fish. And so this kind of gets at a crux of uncertainty and science. It's true that the Flash study has 1 year of data when they're really looking at this, but there's also an accumulation of data over time. And out at the high end of habitat, that's suggesting that there's a lot of flow through the estuary in the fall. It is uncertain whether you'll get a big delta smelt index or not. But at the low end, it's fairly certain that you won't. And so that's kind of the crux of the problem with scientific uncertainty. More flows might be better for fish. It might create a response that you want, or it might not. But low flows will not. And I don't think that that's particularly uncertain or an unscientific statement. So getting back then to the top panel is the time series of this delta smelt habitat index. And it obviously has declined through time, and in fact it took a pretty big step down about 1985, just like the export to inflow ratio. Did come up in the late 90s when things were very wet year over year for a little while, and then declined some more. And so the big issue has been, well, is this a project effect? Is this something that people can manage? And the middle plot suggests that it is. Because X2 is a manageable thing. The state board has regulations around that, and in the fall, when flows are even lower, it's even more manageable. And so what that shows is a nonlinear correlation, as John was pointing to nonlinearities in ecological systems. This is one related to the shape of the estuary. When X2 is upstream of 80 or low 80s kilometers, you have uniformly low habitat suitability, and you can't really discern it too much. If X2 moves downstream of that, it increases fairly quickly, the habitat suitability, and then it levels off beyond 70 kilometers or so, and there's no evidence that you would get any more bang for buck beyond that. So that's kind of the catch. So again, habitat is correlated with abundance because abundance indices and habitat indices are both derived from catch. But that fall like the index itself, the fall habitat suitability has declined, and is related and correlated rather strongly to X2, but not in a linear way. So the key points are just up there to reiterate. Please see the April key points on flow changes. Once again, we do suggest the board model a range of flow objectives that could be incorporated into the water quality control plan. Old and middle river flows contribute to the entrainment risk of adult delta smelt. They aren't the only factor involved. Migratory behaviors and turbidity are things I talked about. But old and middle river flows do seem to drive the entrainment of larval delta smelt. Multiple factors have contributed to the long-term degradation of the low salinity zone, but delta outflow is still an extremely important aspect of habitat suitability for delta smelt.
Okay, so this is the final presentation in the Regulatory and Fishery Agency panel. And, sorry, went a little too fast. So these are the things I'm going to talk about. I have a few brief Clean Water Act concepts to cover. I'm going to spend most of my time talking about new information. And then the final 2 slides will be general recommendations for updates to the Bay Delta Basin Plan. So I'm starting with Clean Water Act concepts really for the benefit of folks who are listening who aren't as familiar with the Clean Water Act, and just to provide the perspective that we have in putting together our comments. So the goal of the Clean Water Act is to restore and protect the biological, physical, and chemical integrity of the nation's waters, and the Water Quality Standards Program is fundamental to achieving those goals. Water quality standards include beneficial uses, numeric and narrative objectives, and an anti-degradation requirement. So I'm going to focus right here on beneficial uses, and you can see up on the screen 3 example pictures of beneficial uses. They include things like municipal water supply, agricultural water supply, and aquatic habitat for fisheries and aquatic life. So protecting your beneficial uses is essential to attaining your water quality standards. Here in California, US EPA has fully delegated the Water Quality Standards Program to the state. It's administered by the state and regional boards. They submit their water quality standards to EPA for approval. And we can approve those standards when we have evidence that the most sensitive beneficial use is going to be protected. So that's it for Clean Water Act 101. And now I'm going to talk about some new information. So just last week, EPA released its San Francisco Bay Delta Action Plan. And in this document, we summarize an evaluation of aquatic life beneficial use protection by Clean Water Act programs. And then we also identify priority actions for restoring water quality and restoring protection for aquatic life beneficial uses. So the primary conclusion after the Clean Water Act evaluation of aquatic life beneficial use is that these rapidly declining fish populations you see up here on the screen are pretty compelling evidence that aquatic life beneficial uses are not adequately protected by Clean Water Act programs. And we're not the only ones to have made this kind of conclusion. We heard it a lot this morning on the invited expert panel. EPA and 5 other federal agencies in 2009 identified the Bay Delta as an ecosystem that had reached the point of collapse, as evidenced by fish populations reaching an all-time low. In the 2010 State Board Flow Criteria Report, the board concluded that current flows are insufficient to protect public trust resources, and CDFG has also made a similar conclusion, noting that current delta water flows for environmental resources are not adequate to maintain, recover, or restore the functions and processes that support native delta, fish. So our first priority that we list in actions in the action plan is to update delta flow standards. We also discuss 6 other priorities, and they include things like advancing delta regional monitoring programs so that we can collect data that help us prioritize stressors in the estuary, accelerating TMDL actions that might be outstanding or need to be completed in order to restore water quality in the estuary. We identify the importance of promulgating new selenium objectives because we do have information that the current numeric objectives are not protective enough of aquatic life. We identify pesticide pollution prevention measures that are necessary. We identify that we're funding, and we also identify the importance of coming up with methods to minimize the formation and transport of methyl mercury. And we also identify our support for the Bay Delta Conservation Plan process. One of the things that we mention in the action plan is just the importance of flow standards as essential for success of other efforts, and I believe Bruce talked about that a little bit on the earlier panel this morning. Okay, so moving on in new information, the next thing I'm going to discuss is recent support for research that's been done over the years in the Bay Delta estuary. A few months ago, the National Research Council's Committee on Sustainable Water and Environmental Management in California Bay Delta released a report, and in this report they review and support the X2 species abundance relationships that you see up here on the left side of the screen. These species abundance, X2 abundance relationships were first identified in 1993. They were reevaluated in 2002, which is the Kimmerer plot that we have up here. And these are the foundation for the current delta outflow objective in the 2006 Water Quality Control Plan. So a few months ago, when National Research Council released their report, they evaluated the technical research behind these relationships, and they conclude that although the mechanisms driving the X2 abundance relationships for some species remain hypothetical, the abundance of a number of different species in the Bay Delta estuary is higher when X2 is farther downstream. So these relationships, X2 abundance relationships, and regulatory actions based on them have received criticism in the recent past, and maybe for a longer time than that, because we don't always fully understand the mechanisms that produce the relationship. So when NRC reviewed these and concluded that despite not knowing those relationships, the statistical correlation is still valid, that leads us to believe that X2 continues to be a valid foundation for water quality standards in the San Francisco Bay Delta estuary. Okay, so the next piece of new information, in the next couple of slides, I'm going to be talking about advances in modeling and some quick information about these maps. They were produced by Delta Modeling Associates, and they're part of the package we submitted as our written comments in the low salinity flip book. They are produced by Delta Modeling Associates using the 3-dimensional untrimmed model. And they show the location, the shape, and the size of the low salinity zone at different X2 values. Up here on the map, you can see when X2 is equal to 65, the low salinity zone is centered or located in Sassoon and Grizzly Bays, and you can see the low salinity zone in the dark blue to the light blue. The dark blue is the freshest part, 1 to 2% seawater, and the light blue is the 5 to 6%. Anything in green is greater than 6% salinity, and anything gray is less than 1%. So we can see here that the low salinity zone is about 7,700 hectares on this map. So one thing I think that's worth mentioning is, 18 years ago when X2 was first identified as the foundation for water quality standards, we could model the low salinity zone just in one dimension, just in the red line that you see on the map showing where X2 is located. So the information we had at that time, you wouldn't see any of the colors, you would just see the line. So we've had some considerable advances that give us a lot more information to work with. So I'm going to show the low salinity zone at a range of X2 values, but before I do that, I just want to remind folks of the location of some important static habitat elements. So in the green circles, you see food sources. That's Sassoon Marsh providing food inputs to Sassoon, Grizzly, and Honker Bays. And the brown circles are areas that are turbid because they're sandy, shallow areas that have high wind speeds. So those are some things to keep in mind as we go through the next few slides. I guess also I should point out, in the eastern part of the estuary there, you go into much more narrow channels. Those tend to be deep and are more clear. So with the higher clarity, we have, as by definition, decreased turbidity and perhaps more exposure to predators for low salinity zone species. And there's also less access to food. So what does the low salinity zone look like when X2 is equal to 85? So you can see the low salinity zone in the light blue to the dark blue. And it's located in the narrower delta channels that are less turbid, so there's more exposure to predators and less access to food. We can also see that the size has dropped in about half of what it was at X2 equal to 65. So then X2 equal to 65, yeah. So X2 equal to 75, we can see the low salinity zone has moved into Honker, Grizzly, and Sassoon Bays. And this is where occupants of the low salinity zone are going to have access to turbidity and food resources. We can also see that this is the maximum size of low salinity zone of the three maps we've looked at. It's about twice the size, a little bigger than twice the size that low salinity zone is when X2 is equal to 85. There we go. Okay. So the take-home messages from looking at those slides and being able to model the low salinity zone in 3 dimensions are that when X2 is greater than 65 or less than 74, we've maximized habitat quality because we have access to food and turbidity, and we've maximized habitat quantity because we have the biggest surface area. When X2 is greater than 85, we've minimized habitat quality and quantity because occupants of the low salinity zone have less access to food and turbidity, and the surface area is minimized. Okay, so the next bit of new information I'm going to talk about is really emerging information combined with decades of research that indicates that the low salinity zone is important year-round. So up on the left-hand side of the screen, you see the springtime X2 abundance relationships. And those abundance relationships are the foundation of the delta outflow criteria we have now. So the State Board 2010 flow criteria report and CDFG's biological objectives and flow criteria recommendations both identify a need to expand those spring criteria or spring objectives into winter months to better protect longfin smelt spawning migrations. More recently, though, most of the work we've seen done is on fall X2, and I'm sure you'll recognize this chart as Matt just went through it, but I'm going to point out some things just more quickly, or I guess I'll be repeating them. But what we see here, I want to focus everyone on the middle chart, is that as X2 moves into the 60 to 70 kilometer range, we see an increase in habitat index. So that's very consistent with what we just looked at on our maps. When low salinity zone is an area where the fish have access to turbidity and food, perhaps they do better. And that's what you see then on the C panel when you move below. Another source of information that we can look at that suggests low salinity zone is important year-round are the fall middle water trawl indices from 2011. We can see Longfin Smelt and Delta Smelt both showed a considerable bump up in their abundance indices from 2011. And I know the invited panel talked about this earlier, so did Pat, but that makes you ask, what was different in 2011? And this chart is similar to the one Anko was showing, but this chart shows the average location of X2 in September and October from 1955 to 2011. And there are a lot of interesting things to point out on this chart. One of the things I think that's most interesting is the median across those years is 83 kilometers for X2. And we can see that from about 1955 to 1975, X2 was more than 83 kilometers in only 3 out of 20 years. But from 91 to 2001, it was greater than 83 in 15 out of 20 years. And we can also see that X2 is greater than 83 in a number of different years that aren't characterized as droughts. You can see the droughts marked as solid red lines along the dotted line. And I think that that's another way to look at the fact that we can manage this. We can change that. We don't have to do as much exporting during those years when we have semi-favorable hydrology. So the last thing I'll point out is just in 2011, you can see the 75 over at the far side of the panel. In the fall months, we had X2 equal to 75. So just as a quick reminder, if I can get this to go, this is what the low salinity zone looks like when X2 is equal to 75. And this is what it looks like when X2 is equal to 84. I didn't have an 83 map handy, but I think it still demonstrates the point well enough that at 75, we had the low salinity zone overlapping with habitat elements that are important to fish. And when we have the low salinity zone at higher X2 values, we minimize that overlap and they have less access to turbidity and food. Okay, so my last 2 slides are really just going to focus on general recommendations we have for updating the Bay Delta Basin Plan. And our first recommendation is just to start with what you have. The 2010 Flows Report and California Department of Fish and Game's recommended flow criteria are very good sources of a place to start to identify alternatives for objectives that you would use to update the plan. We realize you may not end up in this spot, but we think that there's a lot of evidence in these reports showing that you can halt fish population declines and that you could start to increase fish populations. So we'd be interested to see the exercise as how you move down perhaps in percent unimpaired flow to see if you can still halt fish population declines and start to increase them. And then the last thing that we recommend at this point is to connect unimpaired flow to essential habitat elements. So we understand the State Board is considering identifying their new objectives as percent unimpaired flow. And I think EPA supports that approach if we can connect that percent unimpaired flow to habitat elements that the fish actually experience. And that could be a number of different things. That could be turbidity or food abundance or the salinity gradient or temperature. Here up on the slide, we've shown an example of connecting it to the salinity gradient using X2. So what does a net delta outflow at 65% unimpaired flow from January to June look like? Where does it place the low salinity zone? Is the low salinity zone going to overlap with areas that have turbidity and access to food? What does that look like at a net delta outflow of 35%? So this is the kind of exercise that I think will help you narrow down a percentage of unimpaired flow or a range of percentage of unimpaired flow to adopt for your objective, and it will also support why that unimpaired flow will achieve or support that beneficial use that you're targeting. Okay, and that's the end of my presentation. So these are the take-home messages I hope you've heard me say today. Aquatic life beneficial uses are not adequately protected. The X2 abundance relationships have overwhelming scientific support. Resident low salinity species require year-round habitat. Connecting percent unimpaired flows to habitat elements is going to support that objective percent unimpaired flow. And the final thing, maybe the most important thing, is that the Bay Delta Plan needs to provide better protection for aquatic habitat.
Does staff have anything they want to ask before we? Okay.
Thank you. Thanks for the presentations. We appreciate you coming today. for Matt Abriga. I'm real interested, just so everyone knows, in recommendations to the state board on how we might approach this update. And there were some specific suggestions that you had, and one of which was modeling, which kind of touches on a question I had earlier. If to model different objectives, should we take into account climate change? Should we take into account some of the tools that we were hearing about from the science panel that to underlie those objectives?
Yeah, I'm not entirely familiar with, how long of a shelf life the board wants the water quality control plan to have. Obviously, people need to be forward-looking, and that's something you should definitely do. And in BDCP, they have definitely tried to build climate change into a lot of the CalSim modeling and planning tools like that. So yes, thinking into the future, I agree with what was said this morning, that people ought to be having a look at what might be coming. By the same token, for the here and now, depending on how long you expect any given regulation to be in effect, climate change may or may not be all that relevant to it. So I don't actually know the answer because I don't have the context. Sorry.
That's okay.
Actually, this is for Matt as well. The question that I had, you talked about the importance of flow, and essentially low flow means it's not going to work for the species. But how important is it from your perspective to tease out what's the relationship of flow to other factors? Because it may or may not be flow per se, as we heard earlier. It could be flow as it creates, as it relates to turbidity, and you mentioned that as well. How important is it that we have a good grip on what that relationship is?
It is important, and that's one of the purposes of science. I expect that Cliff Dahm this morning was very much correct when he said flow matters, and food matters, and contaminants matter, and all of them are somewhat interrelated, but that's what's not really understood. So yes, it is important. You do have to be a little bit careful with correlations, as we were cautioned this morning. Correlations that hold up over very long periods of time might be a little better than those that don't. But so yeah, I mean, the mechanisms provide future opportunity to do something more efficiently. I guess that's how I see it. So if it turns out that in the fall you can get by with some different amount of outflow if you do something else, that would be great to know, because that's helpful to regulators, and it provides more certainty that you'll get the response you're looking for if you take an action. Unquestionably so.
Okay.
So yes, absolutely, there should always be a pursuit of more knowledge.
I fell into that, didn't I? Okay. Well, thank you very much.
Okay, thanks, guys. Remember to turn your microphones off before you leave. So now we'll have the Resource Management Agency, Department of Water Resources. And they have a few speakers, and they'll be introduced by one of their managers, and then we'll hear a series of presentations.
Are we ready? All right. Well, to kind of paraphrase Aaron, I drew the straw to do the introductions on behalf of DWR. So I'd like to start. My name is Russ Stein. I was just recently asked to assume an acting deputy director role at the Department of Water Resources for the Delta and statewide water management. It's been a fun ride so far, and we'll see how it continues. Today, our scientists are going to talk to you and provide you with information related to the Delta ecosystem, climate change, and uncertainty. As we've heard from many speakers today, there is uncertainty in the science, especially when considering the complex interactions and associations in the Bay Delta ecosystem. DWR experts will discuss that while there has been substantial progress in our understanding of the estuary, the information about the influence of low salinity zone position on fish and ecosystem processes during fall is inconclusive. Habitat is influenced by a complex suite of interacting factors, including salinity, temperature, turbidity, food supply, predation, connectivity among habitats, and channel configuration. The relative importance of these conditions during different seasons to species such as the Delta smelt remains unclear, and additional study is needed to provide a more thorough level of understanding. DWR respectfully requests that the State Board carefully weigh all the information presented during these workshops. It's my understanding that many studies discussed are still in progress, and the preliminary results are currently being discussed. The peer-reviewed products from these studies may not be available for some time to come. Therefore, we encourage the board staff to evaluate the relative importance of the various information presented in this workshop. The Bay Delta Conservation Plan process, which we're all familiar with, has identified adaptive management as a key element to address uncertainties and create successful implementation of conservation measures designed and developed to recover listed species. To address uncertainties, it's important that an adaptive management approach be employed in managing the restoration of the Bay Delta. Such an approach provides the board with the tools necessary to respond to new information as it emerges and provides greater clarity as to the impacts of the low salinity zone and habitat restoration. Adaptive management is so important, it's incorporated into the efforts of the Delta Stewardship Council, the Delta Science Program, the Interagency Ecological Program, and the Draft Bay Delta Conservation Plan. The California Department of Water Resources, the Department of Fish and Game, the United States Fish and Wildlife Service, the National Marine Fisheries Service, and a variety of stakeholders are working together to develop a conservation plan that can be permitted under the Natural Communities Conservation Planning Act and the Federal Endangered Species Act. State and federal agencies recognize that the draft Bay Delta Conservation Plan would create a credible adaptive management plan for the restoration of the estuary. Some of these agencies have even commented that the Bay Delta Conservation Plan has excellent information on predicted future conditions under various circumstances. We need to actively pursue opportunities to cooperatively develop a common science approach among and between the many efforts focused on restoring the Bay Delta. There are several efforts underway that will provide the board new information that could be incorporated into the Water Quality Control Plan update. The new data on biology of the Bay Delta is being developed, and that information is currently under analysis. There are studies that will be concluded in the near future, potentially within the time frame of the current Water Quality Plan update process. DWR would like to recommend that the board consider this new information when preparing the updated plan. Now I'll introduce our speakers. On my left is Dr. Ted Sommer. On my immediate right is John Lehigh, and on my far right is Andrew Schwartz. Dr. Sommer has worked with DWR for over 20 years and has been a leading scientist in the Delta ecosystem and has participated as an active member in the Interagency Ecological Program. Dr. Sommer will give you an overview of the latest science related to the low salinity zone. His presentation will cover new information about flow studies, species biology, as well as review of what we have learned recently about key stressors like invasive species, toxic algae, and contaminants. Andrew Schwartz is a water resources engineer with DWR and has led many of DWR's efforts to analyze the impacts of climate change, or that climate change is having on California's water resources. In 2010, Mr. Schwartz co-authored a comprehensive study of the techniques that have been used in California water resource planning studies to characterize and analyze climate change. His presentation today will highlight a few of the major ways that climate change is already changing California's hydrology and how these impacts could bear upon the effectiveness of flow criteria setting methodologies. John Lehigh is a principal engineer with the Water Resources at DWR and has taken a lead role in managing the State Water Project Water Operations Office for over the past 13 years. Mr. Lehigh's office coordinates with the operators of the Bureau of Reclamation's Central Valley Project, as well as with state and federal fishery agencies in managing the project's water supplies and the forecasting of water delivery capabilities. His presentation today will highlight the major challenges in managing those deliveries against the backdrop of major hydrologic and ecological uncertainty. With that, I'd like Dr. Summer to start.
I think there's some subliminal messaging going on here. All of our screens are flickering.
Uh-oh.
Do you need a second to resolve that? Okay. All right. All right. Well, thanks for the opportunity to present the new material, and do let me know if you have technical difficulties during my presentation. So, of course, our topic today is low salinity zone. We've tried to summarize the available information since about 2009. It was kind of a surprising exercise when we looked over the material, just how much new information there is. So we've got a big 50-plus page document for you to digest. We've tried to address things that we know, things that we don't know. We really tried to explicitly cover things that there's a fair bit of uncertainty about in the presentation. Since it's a large amount of information, we obviously won't cover all of the material in here. So we'll try and give you a summary, but conveniently, many of my colleagues that have presented before me have given about half of my presentation. So I'll get us back on schedule fairly quickly. So our document is organized around a conceptual model that I think many of you have seen before related to the pelagic organism decline. It may be overly familiar, but it is a nice platform to look at things. So fish abundance is affected by many things, including prior generations, the habitat, food availability, and sources of mortality. And we'll try and go into at least part of each of these topics. We're going to start first with the good news. The last time we talked to the board, there was a real and serious concern that there was evidence of a downward trend. So this is the effect of parents. We were seeing subsequent generations of parents with lower and lower abundance, producing fewer and fewer juveniles, which led to the issue of whether delta smelt had lost the ability to respond to favorable environmental conditions. 2011 gives us some hope that the population does have some resilience. You've seen this slide presented several times before, but I think everyone's fairly happy to see after 2011 the highest abundance that we'd seen in about a decade or so. The other thing I don't think any of the other speakers talked about is this has radiated into spring. We saw a fairly good larval abundance as well. Unfortunately, by summer, the effect is somewhat muted, but overall, it gives us some hope that the species does have some ability to respond to favorable conditions. So moving on to habitat, this is obviously much of the focus of the workshop here, and we're really going to focus on mainly physical and chemical conditions, although we'll touch a bit on biological parts in this part of the presentation and in other parts as well. So as you heard from some of the previous speakers, much of the variability in winter and spring for several of the fishes is indeed explained by flow. So this is another version of a graph that Wim Kimmer showed. He used X2, I just show outflow, the same sort of thing, that's my religion. So here are two of the key species, longfin smelt and striped bass. And as Dr. Kimmer described, we see strong relationships during the pre-Potamocarbula period, shown with the dark line and white circles. After Potamacorbula came on board in the mid-'80s. The relationship shifted downward, and now with the pelagic organism decline, we see things shifted further. A couple points based on this. First, we're seeing less bang for buck for a given amount of flow. It takes a lot more flow than it used to reach those historical levels of abundance for some of the key species that we're interested. And second, if you look at the spread of the data points along the x-axis, you see that we've actually had a whole range of spring outflows similar to the historical conditions, but we're not getting the response. So the step declines that we're seeing here are not caused directly by flow. There's something else going on here, and this is a kind of hot area of research now. What exactly is going on that's shifting these outflow responses? Some of the new information that we share here provides a bit of a clue. Wim talked a little bit about this, but a lot of the surveys that these results are based on are done in the low salinity zone and in the delta as well, out in the middle of channels. And one of the hypotheses that we've been following up is to what degree fish have just moved out of the main sampling area. Some of them are still there, but they've shifted to other locations. So one of the examples, and Wim showed this in a slightly different way, is Longfin Smelt, where we plot with the dark line through here over time, essentially the average salinity in the upper estuary across time. And the lighter line down below shows you where longfin smelt were located in relation to the salinity of the estuary. So historically, before the mid-'80s, we saw longfin smelt in more fresh areas, the low salinity zone and brackish zone. And more recently, what they've done is they've shifted downstream into more brackish areas. So they're now more common down in the bays. And again, a lot of our sampling is occurring upstream of these areas. One of the other things I didn't present here, but we discuss a little bit in the document, is Fish and Game has also showed not only are they shifting further downstream away from the low salinity zone, they're also shifting in the water column away from where our midwater trawls commonly sample. Longfin aren't the only species that we have evidence of distribution shifts that may affect the abundance trends that we're seeing. Striped bass are one of the other species. So these are some recent results that we published on juvenile striped bass. Again, most of the surveys that we're conducting are out in the middle of channels. However, there is some sampling that's more inshore and in shoal areas. And what this graph shows that historically, most of the catch was out in the channel area. But what we've seen in recent years is that there's an apparent shift towards inshore areas away from the trawls. Surprisingly, there may be a similar response in delta smelt. We commonly focus on the occurrence of delta smelt in the low salinity zone, principally Sassoon Bay and the West Delta or so, but there's increasingly focus on the North Delta here. We have some evidence that in recent years there's been at least a modest shift up into the North Delta, and the best evidence we have is for Liberty Island. Liberty Island before the late 90s really didn't exist as an aquatic habitat unless you went way, way back. It was a dry farmed area. Some high flow events during the late 90s flooded Liberty Island, creating a large open water of tidal wetlands, including some emergent marsh. And what sampling from Fish and Wildlife Service has showed is that delta smelt moved relatively quickly into this newly created habitat. And what the plot here indicates is that they're actually up in this habitat year-round. The other thing I wanted to note, these are some recent analyses also described in the report. The numbers of delta smelt up in that newly created area are not trivial. We took the data that had been collected in historical surveys, shown on the right side of the graph, that's the low salinity zone in the West Delta, for the long-term stations, and compared those to the occurrence of delta smelt in Liberty Island. And what the results show is that the abundance of delta smelt, or at least the frequency that they are captured in the same sort of gear, same sort of trawl, same sort of time period, are as abundant or more abundant as other parts of the delta. So again, potential evidence of a shift in the population towards North Delta area. Want to note too, it's just not, it's not just newly created habitat where we see cache slough being used. The Deepwater Ship Channel has been a long-term and recurring feature of the North Delta here. This is an example survey from Department of Fish and Game, a whole suite of different surveys here. This is just meant as a sample, but if you're not used to seeing these sort of plots, the circle size indicates the number of fish that are captured. So this is from a spring survey of delta smelt. The colors kind of indicate what kind of condition the fish are in. But the main thing I wanted to point out is also in the channels in the cache slough complex, there seem to be fairly large numbers of delta smelt as well. So the one thing I wanted to convey based on these new results, not that the distribution shifts that we're seeing are the cause of the pelagic organism decline, mainly that these fish are more flexible than we're giving them credit for. The habitat also, as you've heard from some of the other speakers, is much more than just the low salinity zone. We know it gets the lion's share of attention. Delta smelt do use that as one of their core areas, but these outside areas really have to be recognized for both different management things, in particular restoration. This is a really promising area that we've identified where restoration could do some good. So moving on to fall, this is of course the hottest new area of work for flow studies. You got a fair bit of background information about the fall studies. Anka did a really good job describing how the study was laid out. She didn't go into a lot of detail about some of the results. You heard from some of the other presenters about some of the initial results. And there seems to be some confusion about the degree to which the results do show major trends or not. One of the things that's very clear is we did see a big increase in the fall abundance of delta smelt, which made everyone extremely happy. One of the things, though, that I want to emphasize from the fall report is the report that's going to come out is pretty clear on the fact that the results are inconclusive. Again, we're happy to see larger numbers of delta smelt, but this is a direct quote from the report, not just from us. When you have results just from a single year, you're not going to be able to say as much as you'd like. Statistically, we call this n equals 1, which gives us very low power, and scientists don't tend to put as much credence in. The other thing you heard a bit about is that a lot of the work is still ongoing. A lot of the samples and so forth are still being analyzed, the data is still being analyzed. So part of the reason the authors have stated that things are inconclusive is that we just haven't finished the analyses even for the past year. I was pleased to hear that there had been some progress in peer review. I guess Delta Stewardship and Delta Science Program has an initial preview of the peer review. However, the rest of us in the scientific community haven't had a chance to see what the reviewers have had to say about the report. The other thing that we heard about, I think from Anka and some of the others, is one of the things that we were really challenged by in this analysis was trying to tease out the relative importance of fall conditions from the rest of the year. And we heard a little bit about that delta smelt did well year-round. One of the things we identified as part of companion analyses was that conditions for flow and temperature were quite good both in winter and in spring and in summer, which made it pretty tough to try and isolate to what degree fall alone was responsible for what we saw. And indeed, there's good evidence that it's unlikely to be responsible for all of it because the abundance indices for all seasons were already showing increases, which is all a good sign. So this is where, as you heard from some of the other speakers, we really do need to have additional years of study to kind of get a proper signal, and that includes both good conditions and bad ones. And lastly, as Anka pointed out, there's some contradictions in the results. We laid out a series of predictions in the fall report. Some of those predictions were met, others weren't. And so trying to interpret what that means for the overall response is tricky. So as you heard from Anka, she gave a quote from Denise Reed. This is difficult, and this is difficult is not surprising given the whole suite of factors that we have going here. One of the new results that we talk about in the paper is a study by McNally et al. This is an IEP-funded study by the National Center of Ecological Analysis and Synthesis. And really what it lays out a picture of is that the low salinity zone community is really influenced by a whole complex suite of factors. And for this reason, it's going to continue to be pretty challenging to try and identify the relative importance of low salinity zone position in relation to other stressors. And this doesn't mean that flow doesn't matter. It doesn't mean we aren't learning a lot. It's just that the partial and mixed results from last year aren't going to answer all of the questions that we've posed. So continuing on the habitat theme, I think Wim covered a fair bit of that, but we have a lot of information in the report about the various ways that habitat in the low salinity zone and much of the rest of the estuary has become degraded. We have submerged aquatic vegetation, aquatic weeds that have pretty much taken over a lot of the shallow water habitat in the delta. And what you've also heard is that's causing quite an invasion of some of the exotic fishes. Ammonia is an emerging concern. You'll be hearing more about that from other presenters. Harmful algal blooms, something that some of the other presenters discussed. It now seems to be more common than not that every summer, particularly in the later period, we see some pretty nasty blooms. Excuse me. Oh. I seem to have gone back. Oh well. Still poorly understood are contaminants. All right. What have I done? There we go. Okay. Contaminants. Oh, it's going on autopilot now. Forgive me. Contaminants are still something that we're still having a hard time figuring out how it plays a role, particularly for chronic effects, although some of the new emerging information suggests that some of the urban contaminants may be much more important than we realize. So the example here is some recent work by Don Weston over at UC Berkeley that suggests some of the pyrethroids might be fairly toxic in one of the critical areas I just discussed, the Cache-Slough complex. Top-down effects, these are things like sources of mortality from entrainment and predators. We've previously contributed material before. We have a fairly detailed discussion in the report. Also, Matt Nobriga gave a fairly good overview. I will skip right to the new stuff that folks haven't talked about so much, which is predation. This is one of the more exciting new areas that we're making quite a bit of progress about. One of the first examples we discuss in the report is inland silverside. This is a small exotic fish that Bill Bennett identified about a decade ago as a real concern because of their potential to eat larval fish. At the time, though, we didn't really have the tools to follow up on how important this introduced predator may be to larval fish. Brian Schreier from our office has worked with UC Davis to develop genetic tools to find out to what degree these fish are eating delta smelt, and some of the preliminary work that was just published did confirm that in the Deepwater Ship Channel, which is a hot spot for delta smelt, the silverside are indeed taking advantage of delta smelt there. The other key thing, again facilitated by the rise of aquatic weeds in the delta, are centrarchids. These are sunfish and largemouth bass. Here's a comparison from Louise Conrad at her office, who started this project while at UC Davis. And what it's doing is showing the inshore community in the early 80s as compared to the inshore community in recent years. So with the proliferation of submerged aquatic vegetation, what we see is that historically sunfish and bass made up only about a third of the inshore community, and now what we see is they make up the vast majority of the inshore community. So this is a huge shift in the community, and again, likely mediated largely by aquatic weeds. So the question is what this means to species like delta smelt and other fishes of the low salinity zone. To follow up on this, Louise and her colleagues have done a fair bit of work on the diets of these sort of predators. The results have definitely confirmed that largemouth bass are very voracious predators, but the data so far doesn't really provide evidence that they're important predators of some of the pelagic fishes, such as delta smelt. However, we really need to get a better understanding of how flow may interact with some of what we're seeing. Studies that we're describing are from a fairly narrow set of conditions, may not reflect everything that happens in different water year types. So in addition to largemouth bass, we've been making progress looking at striped bass. Striped bass are the apex predator out in the pelagic habitat in the estuary. I showed you some of the results showing that the striped bass are perhaps shifting into inshore areas. There's also been a lot of interest to what degree are these predators having an effect on the community of the low salinity zone and the delta. Eric Lobachevsky, another one of our crack DWR staff, started this work at UC Davis as part of his PhD. He did some bioenergetic modeling, trying to give an estimate of overall population effect of striped bass predation. And the estimates basically show that the trends in consumption fairly well parallel the adult striped bass population. We have finally some overall numbers on what the overall consumption is, but we still don't know exactly what it means for individual prey species like delta smelt, but at least we have a big starting point here. I think Wim also covered some of the bottom-up or food web changes here. As he described, invasive species definitely continue to wreak havoc in the estuary. I don't think he mentioned the jellyfish. Jellyfish are one of the disturbing and emerging invaders in the estuary. What we found from reading about other estuaries, this is not a positive sign for the estuary. It's a sign of habitat shift and overall degradation. As Wim noted, the zooplankton community is shifting pretty considerably. It's shifting away from some historically favored native species towards some dubious invaders. In the lower left-hand corner, I wanted to point out the new kid on the block. These are Siberian prawns, dwarfing the lone threadfin shad that was captured in this particular haul. They came around the time of the pelagic organism decline and have since exploded in many areas. We still don't quite understand the overall effect on the food web, but their abundance is undeniable in some of the areas. And lastly, our report describes some of the work on the benthos, the clams. In particular, Wim described a little bit of the work on grazing rates. We also describe in the report some of the work acknowledging the interaction between clams and flow. One of the patterns that we see is that higher flows tend to push the brackish species, Potamocarbula, further downstream, but one of the other flip sides of that is one of the freshwater species, Corbicula, tends to move in a bit behind it to occupy that vacuum. So it's not all bad news in the food web. One of the things we did want to point out, and that Wim briefly touched on, is that we're getting a better sense of some of the subsidies that are coming from other regions. So I mentioned Liberty Island and the North Delta. This is one of the areas that we've identified as a food web hotspot in the estuary that may be subsidizing the delta. So these are some studies by Gina Benino at our office looking at chlorophyll in different seasons of the year, and the different colors show how different regions of the estuary stack up. And the dark blue bars for each season show you the cash slough complex. And what we found is that chlorophyll levels, in other words phytoplankton, is consistently at higher levels. So the big question is, to what degree does that productivity make it downstream? I've showed you that delta smelt are up in this region and are probably able to take advantage of that productivity. But to what degree can this sort of habitat subsidize downstream areas? Well, as Wim pointed out, we have some indication that indeed we do get some of that productivity. The low salinity zone itself is not very productive. Some of it has to come from upstream. And last year gave us a clue that this can be true even in fall. So one of the things that you didn't hear about the low salinity zone work is that we had predicted that there would be a phytoplankton bloom in fall during the higher flow conditions in fall of 2011. But the prediction was actually that there would be a bloom down in Sassoon Bay near the Sassoon Marsh area. And what actually occurred was that there was a bloom up by Rio Vista, much further upstream. Now, the fact that there was a bloom was a remarkable phenomenon. We hadn't seen a bloom in fall in 20 years. This was probably a really big deal for the food web. So the interesting question was, where did it come from? We do a lot of work up in the North Delta, up in Yolo Bypass, and one of the things we observed is that the bloom occurred immediately after some agricultural flows came down through Yolo Bypass. We don't normally think of agricultural flows as being a positive sort of thing, but I showed you a slide ago that there's a fair bit of productivity up in the North Delta. We also measured high chlorophyll levels at that time, and we think that the flows subsequently transported that productivity downstream. And one of the things that we've learned from our USGS colleagues, based on some spiffy isotope studies, is that the fingerprinting work does suggest that at least a portion of that bloom did come from the North Delta. So that gives us some clues about creative ways that flow regionally can be important and maybe further impetus for habitat restoration. So key recommendations. This is somewhat self-serving, but we'd love to continue to be able to do work to really identify some of the key mechanisms, the factors that affect aquatic species, including flow and some of the additional stressors. We think, based on the work we've described here and some of the work you just heard summarized by Aaron at EPA, that there should be real consideration given to whether or not it's appropriate to have some new regulations for selected contaminants. I also want to agree with several of the other presenters that we need to be preparing now for anticipated changes on the horizon, particularly as Bruce Herbold mentioned, the clam quagga and zebra mussels. We know they're coming. We know they're going to have major ecosystem changes. We need to be able to plan for it scientifically, but also in an engineering context. And lastly, we think that while there's a lot to be learned, we agree with some other previous panels that have worked on Delta Science Program and BCP that there's enough information out there to justify some fairly large-scale restoration projects, particularly if we approach things using some sort of adaptive management cycle that you heard about from some of the other speakers. And with that, I will turn things over and you'll hear about some of our own thoughts on adaptive management and climate change.
There you go. Now it's on? All right. So I'm still Andrew Schwartz, and I'm going to talk a little bit about the impacts of climate change on water resources in California, and I'm by no means a fish expert, so